So this is going to be pretty much wide open. Anything that you'd like to ask the panelists on anything that you heard or haven't heard or would like to learn a little bit more about. Obviously, we had limited time, so I'll go with the first hand. And if you can introduce yourself quickly and what organization you're in, that would help the rest of us. Doug.
Doug Stanley, I'm president of the National Institute of Aerospace. All these charts, and particularly about the 6-time reduction in power, all that is predicated on some assumptions about batteries, obviously, that haven't been in this presentation at all. And to be able to achieve those goals requires some assumptions about power density and numbers of cycles, degradation of cycling, life, that sort of thing. Can you share with us what you're assuming in the models to reach those numbers and how that compares to the state of the art?
Okay, before you answer, Mark, I'll just paraphrase that. The question is for the audience out there on WebEx. Essentially, what are the considerations with regard to battery technology in the brief summary of that question? Go ahead, Mark.
I'll start, but then I'll let Nick jump in too. So actually, if you're talking about the two first objectives for our experiments, which is 5 times reduction in energy used and 10 times reduction in energy cost, actually those don't really matter. It doesn't matter what specific energy you get out of the batteries. Specific energy of the batteries is determining what range you have for the vehicles. And so, for instance, we've got this wonderful sensitivity curve that was developed in cooperation with Georgia Tech, Brian German, where we show if you're at 200 watt-hours per kilogram specific energy for the battery, which is essentially close to where we are today. Actually, the best batteries are getting about 280 watt-hours per kilogram. Then if you take, for instance, an SR-22, a current general aviation aircraft, and use that battery technology that's available, the SR-22 grows in weight from 3,400 pounds to about 12,000 pounds. So horrible, right? If you extend that specific energy of the battery to 400 watt-hours, you'll see a curve that starts way up here and actually at 400 breaks even at the same 3,400 pounds, but for a 200 nautical mile range with the full same payload. So you see that we're at this really exciting point where, yeah, the batteries aren't so great now. But in fact, if you look at Tesla building the Gigafactory, they're projecting that they're going to be about 350 watt-hours per kilogram with their batteries. Essentially, within 5 years, we're talking about having batteries that put us at feasible products. So if we're not developing these new architectures, tools, and doing vehicle studies and tests, how are we going to be prepared? Because it looks like the battery technology is coming on really quite rapidly. But I'll be completely honest with you, because this is one place where Dennis and I disagree, for instance, where I keep saying, you know, all of these system level goals really relate to energy constrained vehicles. And if you want a 1,000 nautical mile range vehicle, we're not going to be able to do that. If you care about somewhere between 200 nautical miles and 600 nautical miles by 2025, we can do that while meeting all those goals. And that's the great opportunity.
So the 400 watt-hours per kilogram gets you to the 6 times motor power weight?
No, okay.
If you count the whole system, when you say motor, it's with batteries and personal fuel, maybe in those trades. Yeah, I'm saying, but how does that compare to where you break even with the battery mass plus the motor and fuel tank mass plus the
Right. So the electric motors are dramatically lighter. The batteries are dramatically heavier. Honestly, I wouldn't say that. I mean, certainly, that's a very reasonable question to do that direct trade. But again, at 200 nautical miles for that Cirrus, that's the easiest example to share with you. But I'm not sure where you keep going to the 6 times goal and
We
where.
had 6 times motor power to weight, but you're just talking about only the motor. I was thinking about integrated, that's one thing,
Correct.
right? But what you really care about perhaps more is the
You-
integrated
you-
weight comparison when you substitute all the power-related systems to the new power-related systems.
Absolutely, and so it really gets into a range question. If you're going to try to count the total energy consumption, and it's absolutely true that in the near term, the next 5 to 10 years, these solutions are going to want to be hybrid electric solutions, and in fact, for the vehicles that we're designing so that you can do 200 miles on pure electric and have these fantastic operating costs that we're talking about in the near term, but when you want to fly 400 miles, essentially you kick in that range extender where you have this small engine, whether it's a small turbine or reciprocating, that's giving you that extra range, but at a higher energy cost.
Okay, thank you, Mark. Take another question.
We have one from the folks out in.
Okay, let's have one out in the WebEx world.
Okay, this is from James Heidemann. It's for Casey. Once the broadband noise is added to the oralization model, to what extent will this reduce the ability to tailor the overall noise signature by varying relative propeller speeds? That is, will the broadband noise overwhelm the tonal noise when the tonal signature is reduced? Does that make sense?
Yes, that makes sense. It really depends on the,
I got you.
okay. Yes, that makes sense. It really depends on the overall level of the broadband and where the peak of the broadband occurs in the frequency spectrum. For approach type of conditions where you're very close to the observers or, at lower altitudes, the propagation of broadband and tonal, is probably the propagation effects on broadband noise is not going to be that significant. But as you go up in altitude, broadband is significantly attenuated due to the atmospheric effects. So it's not just a simple question of overall levels, it also determines the flight path that you're in. One of the things I hope you caught in listening to the oralization is that the character of the noise, even though they all had the same sound power level, your ear was really keying off the frequency content, and that really comes in at the tones. That's well known for rotorcraft, because as soon as you hear a rotorcraft, your perception of the noise, even though those levels may be significantly lower than a broadband type of aircraft, say a jet aircraft, your perception or annoyance of that typically goes up for a rotorcraft for a number of reasons, even though the overall levels may be the same. So what you ask is a very multi-aspect question in that on paper, the overall levels, you might see trade-offs on that, but it really comes down to the perception, and that's really where we key off that we need more ways to evaluate perception of these kind of unconventional vehicles to really make progress in determining the annoyance of them or the acceptability.
Okay, thank you, Casey. Susan has got a question over here.
The first question is fairly simple. I didn't understand on the 18 propellers with the 10 hertz frequency change. Is it 10 each propeller? So like the last one on the list is 180 hertz off of the first one?
Exactly.
Okay.
That was just a demonstration of that. We didn't do any tuning. It could be varied in between, but it was really to demonstrate the degrees of freedom that we now have, and you could really truly tailor some of these noise signatures.
So you kept the thrust, but you just changed the frequency.
Right.
Okay. So my second question is, those are for the isolated propellers, and of course with that wing's really closely coupled, and we know that will probably have an impact on the noise. So how or when are you going to look at that kind of interaction?
Well, that most definitely, you've keyed on some of the key weaknesses. I don't know if they're weaknesses, but there are definitely gaps in our ability to look at some of these concepts in detail. We have a lot of tools that we're able to do it for conventional type ones. They've been tailored towards that. But when we start looking at these unconventional ones, the propulsion airframe integration effects dramatically affect the acoustics. And there's the whole area of propulsion airframe aeroacoustics. We're just in the infancy of it. It's being explored here and at the other NASA centers, Glenn and Ames. This is wide open, and this really has to be integrated into the design cycle. We've just taken the first step here with our perception influence design type of concepts, and that's what we're really excited working closely with our system analysis people, the controls people, to start doing that. It's really a paradigm shift on how we design aircraft.
And if I can add to that, we are working with the Computational Aerosciences branch in 15 to explore some of these interactions and understand exactly what we need in terms of our tool development also, because we're not necessarily equipped, but we might be able to predict a pressure time history. How do we take that and put that into a subjective test environment where we can gain something out of that? We're not there yet.
Actually, if I can say one thing, I think that's a great question, Susan, and I'm so anxious to get to the answer of what the integrated effects are. And I know the acoustics guys are going to cringe when I say this, but if we look at the GL10, it's really interesting, and I'll ask Bill Fredericks to comment on this, but there isn't nearly as much interaction noise as I would have expected. And again, we're using remote RC-grade propellers and RC-grade electric motors at that small scale, so it's not really relevant. But in listening to the videos and the video, I don't notice that much difference from our isolated propeller tests to once they're integrated into the wing in close proximity in flight. Bill, could you comment on that?
Yeah, we've not done any formal measurements or anything, but it doesn't sound much different. Just from a
So I'm pleasantly surprised that there isn't annoying interactive noise that are being captured at this very small scale that is not necessarily indicative of what the larger vehicle would be.
I wouldn't cringe. I think that maybe what you're hearing is some motor noise rather than propeller noise, in which case that's it might be influenced by shielding, but that's it, not aero effects. So this is another area that we need to explore, because our systems tools, we've got very little, if anything, in the way of electric motor noise elements and what kind of, and how we incorporate that in. So that's an area that we need to look at going forward. Thank you for that.
I had a question. I'm Tony Ptotsky. The question I'm wondering in terms of motors. Are these motors like the ones that they use in the Tesla, where you can use it as a motor and as a generator also? And I'm just wondering if that has been explored, whether you could use it as a generator when let's say you go down in altitude, maybe regenerate some of the energy that you expended going up on altitude, and after you do the cruise, you can regain some of the energy that you expended going up on altitude. I just wondered.
Would you like us to repeat the question, Nick? Do you want to answer this, or should I?
Repeat the question for the folks.
Okay, the question is can we use the electric motors as both motors and as generators? And if that's true, does that open up new opportunities for regeneration? For instance, as you're coming down in altitude with an approach, could you recapture some of that energy? I'll give the simple answer and give Nick some time for a follow-up, but the answer is absolutely. These motors can be used either way. The controllers allow them to be used in either way. We can recapture energy, but just realize it's not a win-win situation. If you try to recapture energy, you're inducing drag. And so, yes, when you're trying to slow down, sure, recapture energy, but you would have an efficiency hit if you were trying to cheat.
Going by what Irene was saying is that when you go, when you descend,
Use them as brakes, as regenerative braking, just like automobiles do.
I guess I don't have a whole lot more to add to that, but I think it was sometimes that gets propeller designers a little nervous, and actually, I think it was Tine from Pipistrel, they're designing an electric aircraft right now, had actually talked about just using the propeller, I think, as a brake, and found that it was more effective than I think their propeller designers thought it would be. But still, there is, you're talking about something that is designed for forward flight and trying to turn it into a windmill. So there's going to be some efficiency losses there. If you're talking about having variable pitch mechanisms on it, actually one of the things that we're trying to look for simplicity is to have fixed pitch mechanisms as much as possible on a lot of these props, and just basically to match advance ratio, run them at higher RPM at higher speeds, because you're probably away from the ground at that point, and you're not going to carry that noise penalty.
Right. Well, exactly, because just to follow on what you said, there's a new degree of freedom present in what Nick was talking about, where we can run the electric motors at whatever RPM we want, still at high power, right? So we're trying to avoid variable pitch because of that new degree of freedom that's present.
Well, I was going to say, and the fact that we have, we're already starting at low tip speed means that we're not going to be running up against sonic limits for a little while anyways, as we try to keep advance ratio reasonably matched.
well, the thing that I was going to add, I was involved with the Helios program, and generally speaking, on the Helios program, when they were descending, they were using it as a generator.
Well, that's because it's such an efficient aircraft, they needed to induce drag in some way.
That's what I was trying to say.
Exactly, and actually, to follow on, again, Pipistrel just introduced the Watts Up as an electric trainer. And what's really neat about that is that's a product that's going to be introduced now, even with what the batteries, where the batteries are currently at 200 watt hours per kilogram. And in order to get the most out of that vehicle in terms of operating time, which is about an hour, so to be able to do about 4 sorties as a trainer, one of the things they do is, in the approach, they do brake regeneration. And in fact, they've shared data with us, and it's surprisingly effective and efficient. And they're as a trainer, you're constantly doing that, right? For a long mission or a normal mission, you're not going to use regenerative braking that much. So for them, it's a much more important, significant drain on the battery to be an input to be able to recapture.
Thank you, Mark. We have a question from Dennis.
What has long interested me, and maybe some of you, I'm sure, is personal air vehicles operating from the street in front of your house. And the nominal metrics for these include acoustics no larger than the ambient in a neighborhood at about 10 o'clock at night. Okay. Cost of about $40K or less. Super stall, don't need VSOL. Okay, the street goes on for 100 feet or so. So super stall. And it would be really good if they didn't crash very often. Okay, if we want to operate them out of neighborhoods, it's far better if they don't crash too often. So the question is this the technology that you currently think is the best bet for that kind of a mission? Or if not, what do you think would be?
Okay, but I'm so anxious to answer it. So Dennis said, hey, he's been wanting people to develop new technology solutions for personal air vehicles for a long time, and that fundamentally they need to achieve incredibly low acoustic signatures so that they can operate in close proximity to neighborhoods. They need to be incredibly low cost to be competitive to current solutions. They need to have extreme stow capability so they can take off and land almost without any infrastructure, and they need to be ultra safe, so any rational person would actually want to fly. And his question is distributed electric propulsion the technology to get to achieve those 4 objectives? The answer is absolutely yes. And the reason is for the acoustics, I think we're showing that there are compelling new degrees of freedom. And if we can keep the vehicle small, because no matter what, noise is going to scale to the gross weight of the vehicle, right? So we need to keep the vehicle very small if it is going to try to operate in close proximity, but then you want to do everything else to make it even quieter. And it's these new wonderful knobs that we can turn. In terms of the operating cost, again, you want to keep the vehicle small, but really, if you look at general aviation with that one chart that I showed, 50% of their total operating cost is fuel cost. So aviation fuel is expensive, and the current aircraft are incredibly inefficient. Again, we're talking about a 10 times reduction in that cost, or 4 to 5 with amortizing the battery. In terms of safety, yes, having propulsion system redundancy, especially for operating at that low and slow condition, because you're talking about extreme stow capability, you have to have propulsion-based control. You can't just throw big wings and big tails at it because you want this super compact vehicle. In terms of the last one, extreme stow capability. So we've been doing a really cool aeropropulsive study. I haven't shown the results yet, and I want to cite Joby Aviation and Nick, who's been doing fantastic work on this. We can beat your favorite aircraft, the Custer Channel Wing, and that is at 61 knots. So we've got our 31-foot span wing, okay, with 300 horsepower going into it. At 61 knots, it's a CL max of 5.5. At 45 knots, same exact power going into it, but the reference speed decreasing, it's a CL max of 7. Just because the reference velocity versus the induced velocity is changing, right? The reference velocity is getting smaller, then induced velocity is essentially staying almost the same. You go down to 20 knots, what's the CL max of that vehicle, Dennis? It's 19. So all of a sudden, we can achieve these incredible. You can be talking about taking off and landing with 20 knots with far less power than you could with vertical takeoff and landing. Well, in 20 knots, in 20 feet, I can accelerate to 20 knot with a thrust-to-weight ratio of 0.5. I can still do a helipad takeoff and landing capability, but with half the thrust that I need for a vertical takeoff and landing aircraft. So you betcha this is the right technology for what you want to do.
One other thing I'd like to bring up, there are additional factors to consider for a street landing PAV that perhaps
I didn't say street landing was a good idea, by the way.
I mean, there's this kind of last 50-foot problem. The one very nice thing about airports is that they're a relatively sparse environment for threats. People are, for the most part, going to be doing very predictable things. And this idea of uncooperative sense and avoid can essentially be, if I see something that looks out of place, I just am not going to land, and I'm going to come back around until things look like they're in place again. On a street, it's a much more significant problem. What is, my street changes every single day. I don't know what's going to be there one day versus another. So solving that particular problem, I think, is going to be another significant challenge for the street landing PAV. And that's not to say that distributed electric propulsion doesn't offer a lot of these STOL and affordability and other types of benefits. So,
and I don't believe that we should ever be operating flying cars from every street and every cul-de-sac. I would say this instead, and we're starting to do comprehensive studies where if we can keep it to these vehicles to a 50-foot helipad type of environment or something smaller than a tennis court, then there's places where infrastructure could immediately show up. In fact, one of the studies we're doing now, we're looking at every single clover leaf on the highway system, which is just sitting there vacant, and it's about 100 foot in diameter. where you could have at every one of these cloverleafs, which is actually where the population exists, right? That's why there's a cloverleaf off-ramp to the highway. You could have 4 helipads operating at each one of these cloverleafs. And you could implement that infrastructure for trivial costs and have it in proximity to highways which are already an ambient noise signature that people accept, and we can be lower than that. So I think there's wonderful ways, if we can keep this to an extreme stoll capability, to let the infrastructure spontaneously develop in ways that make a lot of sense.
Okay, I have one as I'm walking over to the other side of the room, and that is for Irene. What do you think the society acceptance is going to be for climbing into a vehicle? We're not doing it with cars yet. Punch a button, maybe in a few years, and we go, and hands off the wheel. What's going to happen with these aircraft?
So that's a good question. Societal acceptance. Well, as soon as we start having cars when we get in the morning and say go to work, and meantime I open up my Wall Street Journal and I enjoy reading it, that becomes part of life, right? Just like right now, people say, well, I won't get on an airplane unless there's a pilot, for one simple reason. They have a skin in the game, right? They don't want to die, I don't want to die, so that means that they're going to be a better pilot. I want a human in the cockpit. You get enough of the Asian Air accidents where 3 very experienced pilots sat there and couldn't do the rudimentary, basically flying of the aircraft because somehow they missed all the displays and all the alerts that told them they're a little bit too slow, or not so little, coming in for a landing. People start accepting the fact that under normal conditions, if my car can drive me safely and can self-park, why not? Especially if you start with something that doesn't fly 300 feet up in the air, something that starts fairly low and say, come on down, and everything is nice and safe. So I strongly suspect that's going to be part of the natural progression.
Mark wants to go out 10 to 20 years for batteries. So let me go out 10 to 20 years for what's happening in the streets. What's happening is the U.S. has passed peak car. We're tele-traveling, telecommuting, tele-everything. The auto market is somewhere around $1 trillion a year. That's the pave market. If we went to pave, we could not have the costs of a lot of roads and bridges at $20 million a mile and so forth and so on. And so what you're then looking at is a neighborhood composed of a bunch of small places to put VSTOL things in. The change to this, the tele-everything beyond the IT age, is the virtual edge. And everything's going massively that fast. I mean, 10 to 20 years is going to make a really major difference. And yes, I think we ought to, work aero things in the 10, 20, 30 years out. But you have to project not just your particular technology and, technology state of play that far out. You have to look at where society's going. You have to look at the markets. You have to look at everything.
That's a question.
I want to answer it. This is great. So the question that Dennis asked is, hey, we're entering this period where we're past peak cars. How many cars will be produced per year? There's going to be new operational models of car sharing and telecommuting that's going to fundamentally change what mobility means to society, and society's going to adapt to it, right? And there won't be this huge, incredible amount of money that's spent on highways and roadways when there's an alternative that doesn't even need them anymore. So Dennis's point is, hey, you can't just look at your own technology. You've got to look at how all these technologies are coming in to fit to a new societal whole. Completely agree with you. And actually, the wonderful thing is that from what I see of these different factors coming in, they're all working together synergistically to promote the kind of vision that we're talking about. For instance, you're talking about car sharing. So instead of you buying a car, all of a sudden, there's this crazy idea, if you live in Mountain View, California, That Google's got 100 self-driving cars driving around, and anytime you want one, you bring up your iPhone, say, pick me up. You drive to where you want to go, and you're there, and you don't even need to own a car. Well, guess what? That's not 20 years from now. That's next year. Google's putting this fleet in operation in Mountain View with 100 cars next year. So how does that play into what we're doing? Well, this car sharing idea of not individual ownership is the single most important thing to make these electric vehicles make sense, because electric vehicles don't make sense at low utilization. That's why we don't all have electric cars, unless you're a zealot, right? Like me, but for electric cars. They make sense at high utilization, where essentially you're taking those expensive batteries and you're using them every day at as high a rate as you can to recharge them. Same for us. As we can get to high utilization models, instead of you paying $150,000 for that two-person PAV that has incredibly expensive batteries, it just shows up. When you need it, you use it, then it goes to the next person. And this directly plugs in to another piece of societal change, autonomy, right? Where you don't need the experience, and for that vehicle to redeploy, instead of having a deadhead where with Dayjet, 2 pilots had to reposition that vehicle to get to the next paying customer, this vehicle can reposition by itself. Telecommuting now, also, it's coming. Instead of you driving to work 5 days a week, you're probably going to drive to work 2 or 3 days a week. That directly plays into these kind of vehicles. You don't own them, you use them when you need them, they show up. Incredibly technology convergence that's taking place. I think they're all enablers for what we're talking about. So it's not a competition, it's all pointing in the same kind of direction of on-demand capability with high utilization vehicles that are incredibly clean and able to serve the masses in fundamentally new ways. We will not have private ownership models being successful in the future, probably.
I just addressed a comment of the person on your right who was worried about all the impediment, that it's in the streets. That's something you have to be.
The question is, will we be post-children and post-dog at that point? So.
And I would only argue, Mark, that it'll be a Android app if Google has anything to do with it. So,
I'm a believer that Google will rule the world, so yes, you're right.
Okay,
I have a two-part question. I'm wondering, as you are presenting this material to this cross-director forum in the architecture space, what disciplines are not represented here that any of you all think they need to step up? I'm thinking safety, I'm thinking materials, structures.
Actually,
What else?
One that I was thinking about from this last conversation, weather. When we get into our cars, we assume an almost all-weather capability. We get used to this dispatch reliability that is essentially one. So we want to be able to just jump in our car and go in all but the absolute worst weather. Flight is far less forgiving of that. There is a whole level we talk about, where does decision authority lie? Right now, a lot of these light aircraft, certainly aren't certified for flight into known icing. And that takes power, that takes a lot of smart design, so that a lot of that is not represented here. There's decision-making that right now is reserved at the pilot and command that says, do I go, do I not, do I execute this approach or do I not? Where am I gathering that weather picture? How does the probabilistic change in what I am gathering affect that decision? I think that is one of many that is probably not represented.
Well, I would not so much argue against that, but I don't think we've gotten there yet, because frankly, that's all under the auspices of autonomy. When we talk about true autonomy, we're talking about integration of all the information sources that are out there, including the weather, including the health of the vehicle, including the capabilities of that particular vehicle, et cetera, et cetera, et cetera. So it's just too premature in some respects, right? It's one of those, it's a development, and it's not just for these vehicles, it's for a number of any other vehicles. It's the same thing, is we start to walk before we run. And so let's start not only the controls, the flight controls itself, it's not so much that it's easy, it's not, but we know how to do this, right? It's the next level in the next iteration. What if I decide to change my mind, and instead of going to the store, I want to go bypass and, go pick up food before I go to the store? Do I need to make that calculation, or basically do I tell, Charles, take me, so to speak? And those are and that's fairly easy decision-making, right? We're not talking about what happens if there's an accident, there's some kind of obstruction, there's that last 50 feet, there's a dog in the street. I mean, that's all auspices of autonomy. When you start talking about UAVs, and this is before anywhere, we're going to start landing in a neighborhood in the driveway, we're going to start doing this with much smaller vehicles. The package delivery that Google and Facebook, and I'm sure the Facebook will get into it, Amazon are talking about, you're talking about, okay, I'm going to deliver this package, but how do I land? Where do I land? Do I land somewhere, 300 feet away from my house? Well, that's not that convenient. I want the UPS guy delivered to my porch. So when I deliver it to my porch, how do I know, not only is it the right house, but how do I know there's not somebody's dog sitting there or a kid decided to reach up? That's the last 50 feet. That is being covered under the auspices of autonomy. That is controls.
And Google's answer is they drop it on a line and let the package slowly descend and be recovered.
Right, and Google, but they also assume that I'm there to receive it. And I'm not home
No,
when UPS.
they'll just drop it off. That's what they're doing in Australia already. So we may think this is 20 years off. Google's already doing this in Australia with operational experiments. I want to throw in one more thing. So we've got acoustics, control, aero propulsion. What I'm really excited is aeroelastics and structures is coming to the table with us starting this year, today with our new CAS effort. And what's so exciting there is, again, new degrees of freedom. We have a constant weight vehicle that has extreme span loading. What can we do with that? We get to start answering that question with our experts. Really exciting. But we need to pull in the materials guys too, which unfortunately we don't have enough money to. But think about it. As Doug pointed out with batteries, 40%, just like the Tesla car. Tesla had to redesign cars from the ground up to these high mass fraction battery. 40% of the Tesla is basically a battery. Same with us. Aircraft, 40% is going to be batteries. Where are these material guys with these multifunctional batteries? It's 40% of the weight. If we can start blending that with a structure, huge gains to be made.
Comment too from the controls perspective, because of aeroelasticity, but also the environment that you're flying in. So the lower atmosphere is quite turbulent, and so maintaining control with a small vehicle in a very uncertain environment is a major challenge. Part of safety and part of performance and part of acceptability of automation. So the notion of coupling control into things like gust load alleviation, making ride quality satisfactory, so ride and maneuver load alleviation type of things are factors that also I think are really important in getting viable and acceptable vehicles that will meet the market needs.
Right, and we don't want to dump horrible problems, so the first thing we're doing is we're trying to go to high wing loading solutions that can provide propulsion control, right? Because if you're going to be flying slowly, the last thing you want is a huge wing at low wing loading, so a small gust comes and you're upset. We're going to these high wing loading solutions, which also gives us cruise efficiency, and lots of propulsion control, so as you fly slower and slower, those propulsion devices are more and more effective compared to that reference velocity. So we don't want to dump all the problems on them, but make their life easier, right? Irene, you see that all the time. We're always making your life easier.
It's just a point of, it's an optimization. There's a design trade there is where you go. Design space is opened up.
And there's never been a better, bigger design space to explore than this.
So one of the things that is also coming up a bit from, we had some discussion on, what are V speeds for approach and why is this safe? And there's actually an opportunity here to make Irene's life harder. because part of what is, part of the reason why we carry all of this margin, the stall margin with us on approach in terms of speed is because of gusts. Well, if I have an ability to sense gusts, maybe I can approach a lot slower. If I have the ability to very quickly increase the flow over my wing, hopefully without undue acoustic penalties, then maybe I can use this approach and get into a lot tighter spots. So there's, I think, some opportunities to certainly make our controls folks and our acoustics folks' life a lot harder. So that's what makes me sleep at night.
I've been told Aeroscience is going to come in and help me out with some flow control for ride quality, so we're all set.
So that's another place where aeroscience, structures and aerosciences can come in, is distributing multifunctional control of surface and structures. So more back to more what we did back in the work tried to do back in.
And that's why, in my mind, we need more of these opportunities where we're all forced to work together instead of in our sandboxes. For instance, with flow control, I loved circulation control. Dennis brainwashed me early on in my career until I heard one of the wind tunnel tests. And I realized that if they want great circulation control performance, they burden the acoustics guys with a nightmare of a problem. We need more problems where we are working together so that one systems guy doesn't create a horrible problem for the controls guys. We really want to get to these more integrated product type of team opportunities, which the CAS project gives us. That's why it's so exciting to see the direction that ARMD is taking, because I think they're understanding the opportunities are for us to work together and not in our individual sandboxes anymore.
Okay, Ed Hogg, Northrop Grumman, and I support the Safety Critical Avionics Systems branch and do some work with prognostics and decision making on the electric edge. We have and the edge was the spinoff of the AirStar rapid evaluation class for doing structures research for a wing. But when that funding dried up, we had some continued work with a group at Ames that do battery prognostics. And this is a $20,000 class vehicle. Would there be any interest in and we have a single propeller in this electric aircraft, and it'll fly for about 10, 15 minutes, 40-pound vehicle. Any interest in replacing one of our wings, or I guess both wings, and with a distributed wing? I don't know how that would get through the Safety Review Board. That's what I'm wondering about, because we didn't change any mold lines.
I'll be happy to jump in. So, and Bill, is Dave here? So Bill, correct me if I'm wrong. One of the neat things, again, with spiral development is it lets us answer a lot of questions that we wouldn't normally answer with a system study. And so Bill and Dave have been going to the ASRB here at Langley, and the ASRB is incredibly helpful in helping us to quickly be able to get permission to test these new technologies. So I think it's these kind of spiral development efforts which engage other parts of the center that typically systems analysis would have nothing to do with ASRB. Now we've developed this fantastic cooperative arrangement. Bill, do you have anything to say about that?
I guess the question was, is it possible for the ASRB to approve vehicles like this? And I would say the answer to that is yes. However, yeah, I mean, it's just a question of money. So we get more money, we definitely want to do more testing. So, yeah.
And ASRB has already approved one distributed electric propulsion vehicle in the air. This next CAS project that is a large-scale, several thousand-pound aircraft will go through the Armstrong version of the ASRB, and we've already been interacting with them. We've been interacting with the test pilot, who's already given us his set of requirements. So we're confident that we're going to be able to successfully be able to flight demonstrate these technologies even before anyone else. We will have the first distributed electric propulsion manned demonstrator.
I'd say one potential thought, particularly with Airstar, as I recall, it's a lot of alternate control modes, and then how does the pilot react to that inside of the trailer? I mean, I think evaluating pilot reaction to for the single lever control problem here and all these alternate control modes and those flight dynamics might be a possibility. I mean, certainly would be an interesting test case for that.
So this is Jeff Bartholomew from OSAC-B. Despite your assumption, Mark, the distance between Los Angeles or San Francisco and New York is still over 3,000 miles. So it seems to me that on-demand mobility is not quite there yet in terms, I mean, if you want on-demand mobility, it has to apply to short distance and long distances as well. So I'm curious, of the technologies you've been talking about, what does scale up here? What is it that you can carry to the larger scale in the work you've already done?
Okay, so I've got a question back for you, JF, and that is, how many trips are flown 3,000 miles across the country versus how many trips are taken at 200 miles or less?
That's not what the question is. The question is, you're trying to have an on-demand, I can go from here to there, however I want, on demand, essentially. So anything, you're going to have to cross some long distances. Whether you do it a lot or you don't do it a lot is a different issue. But anything that what you do that you can actually scale up. This is not a critique of your assumption. I think you're starting at the right place. And I think you're going to be resolving a lot of the transportation problem by looking at that 200 to 600 nautical miles. But then how do you scale it up? What can you take from that to the bigger scale?
Well, it depends what you mean by scale up. If you mean scale up the vehicle size to 737s and beyond, that's not the challenge. I mean, yeah, we have to prove it, but I'm pretty confident that these technologies will scale up and still have meaningful impacts. It's just that a 737 is pretty dang good compared to a Cirrus SR-22 because it's had billions put into it, and a Cirrus SR-22 has had 10 million or 30 million. So there's a huge difference in the baselines that you're comparing it to. But so in terms of this technology scaling across vehicle classes, I'm confident it can do that. But if you're asking this technology to scale across range classes, it's not well suited to that. And I fundamentally have not proven to myself that these, even as hybrid electrics, that this technology makes sense for anything beyond 600 miles until batteries become incredibly good. And it's just not a good fit for energy-constrained electric propulsion to map into long-distance travel. They're not compatible.
So let me ask you the question differently. 25 years down the line, your fleet, that still will have to carry me across the country and some others as well. What will it be made up from your perspective? How would you
25 years, that's an easy answer. I can tell you with very high certainty. 25 years, it's going to be essentially the same fleet. Right? The same aircraft are going to be flying. That's the way. It takes forever to change the fleet because they're incredibly productive vehicles that are very good at flying long distances. I don't think that's the problem we need to solve. They're already really good at it. The problem is that for trips for 500 miles or less, there's no good transportation option. Because guess what? I just came back from Cleveland. I had to fly all the way down to Atlanta to get home. And it was even worse the other way. So, I mean, this indirect routing that hub and spoke does is insane. It's insane in terms of my time. It's insane in terms of emissions and energy consumption. It's insane in terms of productivity. We've got a great long distance solution. We don't need to fix it. We've got to fix the short and midterm solutions.
And I'd just also mention that, I mean, the L over D of those long distance transports, they have enough money and mass that they can throw at pretty good high lift devices, so they can get closer to a cruise-sized wing. They don't benefit as readily from the use of distributed electric propulsion. I mean, there are certainly, I think, other technology areas that could come out of autonomy. I mean, certainly single pilot operations was targeting some of the crew costs and other things. But yeah, I don't know if you'll necessarily see a DEP type wing on anything a whole lot bigger than an RJ class of vehicle, just because the L over D isn't there.
Yeah, I would just say this. I'm convinced I mean, the 737 has an average stage length of 535 miles. I'm positive that we could design a regional turboprop that can beat the 737 for that average stage length or shorter with at least 20% improvement to their direct operating cost. So, I mean, the question is where they're flying. And on the flip side, if we tried to compete with the 737 on a long distance route, the distributed electric propulsion is such a loser, a complete loser.
I just want to comment, and additionally, don't forget the benefits of more electric. All the airframers are throwing money at that now, and they're only having their benefit from that because they're still human-driven systems. They're still human-commanded. So all the autonomy and the new certification will those are earlier technology paths, I think, that'll affect the continental flights at least.
Okay, we'll take maybe 2 more questions.
How you doing? My name is Quincy Williams. I had a question. I was wondering what region of the country are you targeting for these types of airplanes? I saw you had a picture of Virginia, you know, and around this area I could get a flight to probably DC for $50. So, but I've heard of places like in South Dakota where it's $700 just to fly something like 200 miles to the nearest airport. What's the best place for something like this type of technology?
These are such great questions that I'm sorry I'm hogging it, but I really want to answer this. So the question is what's the best place for these kind of technologies and operations? And especially in my mind, when you ask that, it's where are the best early adopter markets where this technology could start to flourish, even if it's a little bit expensive in the beginning. And the answer is look at where the hypercommuters market is taking place, because over the last 10 years, the number of hypercommuters has increased by 79%. So again, I mentioned it in my talk, 600,000 people commute more than 200 miles each day. Where are those markets? Silicon Valley, Los Angeles, Houston, and actually DC is another one of them. So there's these wonderful opportunities where people are already trying to do these medium distance trips every single day. Now, I think what you'll have is this convergence of not only where those frequent travelers are, but other factors such as Nick pointed out, which is weather. You know, we're not going to solve everything in the next couple years. We're still going to have issues such as de-icing. So you want to look at where the early adopter markets could flourish in terms of weather as well. And again, Los Angeles, Silicon Valley, Florida, maybe some of Texas. So there's these wonderful opportunities, and my answer is the first place this is going to happen is the Silicon Valley, because I live there. I know it's several $1 million to own a house in the Silicon Valley unless you live in Manteca. So if you look at some very bright PhDs that live at NASA Ames, guess where they live? Because they're not working for Google, they live in Manteca because they've got to be able to afford a $400,000 house. That's a 2-hour one-way trip from Manteca to NASA Ames each way. And they do that today because that's the only way to be able to afford a $400,000 house instead of living in Mountain View, which $400,000 would give you a closet. And so it's the convergence of weather, where the people need it, economic factors such as housing cost that are all going to come together and probably say it's Los Angeles and the Silicon Valley are the best early adopter markets.
Okay, thank you. Well, let's just take one more. Well, I'll ask it then. Casey. We have a lot of tools for acoustic prediction. What's the state of our predictive ability for doing tilt rotor or tilt wing analyses? Because in this case, we use the propeller aircraft or propeller prediction code. For rotorcraft, we might use overflow. What do we do in between?
That's a good question, Steve. We have a number of tools, and they've been worked in different programs. The rotorcraft area has really progressed a lot of the CFD tools, particularly for rotating blades. And a lot of that technology came out of some of the earlier programs that DARPA had, the quieting helicopter. That really advanced the use of CFD on a regular basis for a lot of the rotorcraft problems. But using those for the conventional ones, again, it's crossing over these barriers that are not necessarily technological, but having people the capabilities to use those in other disciplines. That's what's really been evident in creating this team, that we're starting to use those. Now, to answer your question about, what kind of tools would we use for a tilt wing that has propellers on it, it's kind of halfway in between. One of the big areas that's hard to evaluate on that is the transition, and some of that came out through rotorcraft when they had the tilt rotor. That's a very difficult problem because you're doing the full regime on rotor blades and in a rotational frame, as well as the downwash and the influence on the total aircraft. A big hole in that is the computational power and the selection of even the tools that are appropriate for acoustics. A lot of it we've been able to do for the aerodynamics, but to really calculate the noise and what parts of the noise are important. Is it the tonal? Is it the broadband? We're very much lacking in the broadband. So to answer you, it's kind of in the infancy right now until we can start really evaluating what the important sources are, and that's where this human perception idea comes in, is starting to pinpoint where the really high totem poles on the noise sources are, that we can start attacking specific tools. But currently we have a number of them that we can use, but all areas need to be advanced, and I think integrating it into this has just really highlighted where a lot of those are. I hope that answers your question.
That's great.
Great.
Thank you. Thank you very much. And I'd like to thank all the panelists for their presentations and time this afternoon and answering our questions, as well as you all for coming out.